I didn't have a super lot prepared today, but obviously got some. I put together some slides just around some of the spectrum analysis, real-time spectrum analyzer stuff that we tend to talk about from applications and some technology points of view. But honestly, happy to discuss anything you guys want to discuss as well. So feel free. You're not interrupted. Just jump in and ask whatever you want to at any point, and we can keep chatting. So I guess just to kind of start off, I'll my name is Chris Armstrong. I'm over at RIGOL Technologies, and I've been here about 10 years, and over that time I've done a kind of variety of I talked to a lot of folks about different types of ham radio work and analysis and applications. Been down to the big Hamvention in Dayton, Ohio a few times myself, and always appreciate the opportunity to chat with folks who are interested in this sort of stuff. And we're always trying to bring new technology to market that in a kind of affordable way that we think it might be interesting to people working on their ham radios. So that's kind of the quick background. And then we can chat a little bit about what we talk about today in terms of these kind of applications and interesting technologies. So what we're looking at there obviously is that's an FM signal. Someone called it before, I think. So looking at just local FM station actually on the real-time spectrum analyzer with a density plot and then a waterfall chart as well, right? So pretty typical sort of just analysis, but the speed and the measurement capability, I think, is a good starting point for a discussion about what's possible now and what's interesting. So when we talk about applications in this area, there's sort of four main ones that we think are interesting for folks, and then a couple of advanced ones that we'll hit on at the end. But I think the most interesting stuff is really around, just from a technical perspective, is around those high-speed captures and those spectrum monitoring type applications. So we'll start there with some with a little in-depth view about how I go about capturing signals with this type of instrumentation. So when I start, obviously the kind of easiest way to start looking at signals is with a nice wide swept mode, right? Especially if you are looking for something you don't know exactly what band it's in, right? So we can capture a nice wide spectrum there down at as fast as a millisecond with one of these instruments that are doing relatively high speed sweeping at this point. Can access markers and peaks to look at different signals with a max hold as well. So a good way to kind of capture incremental signals and look at them, and then find ways to dig deeper into each of those. Right. So have RBWs from 10 megahertz down to 1 hertz for different kind of analysis views. At this level of a sort of high speed initial scan. Then what I like to do is go into real-time mode. And in real-time mode is kind of what we were looking at there a minute ago with the FM signal. And these instruments, that gives you up to about a 40 megahertz wide swath you can look at a time. So you can capture different bands and different areas there. And here kind of is where I think there's some technology kind of worth discussing, just because the nomenclature might not be familiar to everyone. Right. So we talk about setting a wide RBW here for what we call lowest POI, or 100% probability of intercept. So this is sort of the key, one of the key specifications for kind of real-time analysis is what, how short of a signal in time are you guaranteed to accurately measure in power every time. So that's the 100% probability of intercept for accurate power measurements. And the wider you set that RBW, the more accurate those power measurements become. So here you can see a fairly wide RBW, which gives you can see much more accurate power across the span, because we're working on the assumption that those signals are all relatively the same power, but it gives you more accurate power measurements across there. Or once you find what you're looking for, once you measure it, you can zoom in with tighter RBW, which gives you a little more fluctuation in power levels outside the specifications, but gives you a broader or a better look at the individual signals, right? So we can now see that these are, hey, here's a Wi-Fi signal in the 2.4 gig channel, and these little peaks here are Bluetooth, access connections, some Bluetooth device, probably a mouse or something, testing different channels to optimize its path. Right, so that allows us to, really kind of decide between accurate power with a wide RBW, or tighten that RBW down for I think better visualization, but a little more, a little less clarity on the actual power levels of those signals. So that one of the ways that I do this is that this kind of RBW2 setting we call, where it's really gapless. So because the way the analysis tool is overlapping. So I think it's an important concept. Let's, if it's all right with you guys, I'll dig into a little bit of the technology here and why that's the case. And so when we're talking about an instrument like these particular instruments, these are the real-time spectrum analyzers here from RIGOL, what we're actually doing is we're pulling in that data all in the time domain, right, with the electronics, and we're capturing it and then converting it into with a fast Fourier transform into frequency space, and then posting it up on the display as quickly as possible, giving us a sort of quick time overlapping, very dynamic view. And so here are each window of the FFT capture for different RBW sizes, right? So you can see as the RBW gets higher, we focus on a shorter period of time, and that allows us to make better accuracy measurements, but also leaves us with gaps, right? So in this mode, these instruments can do can do a capture every 6.83 microseconds, right? So that leads to, we can use the wide RBW windows, RBW1 and 2, so the signals are always overlapping, so we're never not using any data, so we're never missing signals. But then you can also tighten down all the way to 6, which gives you the more accurate in power. And so why is that more accurate in power? Well, the trick is that when we're talking about short time duration signals like those Bluetooth access points or more exotic signals, you've got, if you have a signal that is only on for 3 microseconds, right? And it's in this range here. Well, for it to be accurately measured in power, the RBW window has to be fully encompassed by the power, by the active RF signal, right? So if the signal is only 5 microseconds wide in here, well, you'll see it on an RBW1 or an RBW2 setting, but you'll have attenuated the power because of the time that you were looking at the signal with the power off. Whereas the shorter RBWs, as long as you're capturing it across the whole span, you'll get you'll get the full power measurement. So that's kind of where the RBW of in this case, I think the optimal setting is about 7.45 microseconds, which is because that signal, that 7.45 microseconds on RBW6 is wide enough that it has to either be caught completely by the first or the second capture. So it's about this wide, right? And so by either being caught by the first or the second, we can always make an accurate power measurement of that signal.
Yes, we're not right there. Just point your face. How about that?
So cool. Is that a question or comment? Go to town, guys. No?
I would just like to say that if anybody's wondering what might be on my Christmas list, this would be a good opportunity.
There you go. Well, that's kind of that's the beauty of what RIGOL does here in this market is we keep bringing these prices for these kind of capabilities down. You can get a yeah. So a little different way to visualize that same technology, I guess. The 6 RBW settings from the your skinniest to your widest, and the associated sort of POI on a 40 megahertz span. All right, so you can in this case the signal's static enough that all the powers are the same here because it's longer than the widest 30 megahertz signal. But you can kind of see how the spread of the frequency domain and the narrowness of the pulse, just keep in mind that those are all the same signal, just being looked at in different ways with a different filter setting. Cool. So I think once I use those sort of real-time techniques to kind of isolate signals, look at high-speed interference signals, things that are bugging me, even really fast modulating or low duty cycle signals are pretty easy to catch with those sort of capabilities. So once you catch those, then I tend to go into a mode where I try to isolate some of those signals. And this is where things like frequency mass trigger become important, because I can go ahead and just trigger on those peaks. So since I'm feeling bold today, I'll do it on my instrument here. Let's see. So I go ahead and put this into, well, I first put this in the frequency mass trigger mode. There you can see I'm triggering on different parts of that signal. I can move the mask to capture only portions of that signal that are in a certain spot here, kind of focusing on the green and the green mask, right? So you're able to now it's triggering slower because you're able to isolate signals that only appear in that one quadrant. So an easy way to kind of capture signals and isolate causes of interference, right? Because then I can I often do something like this, and then I'll set the trigger out mode on the analyzer, or use the IF output and put it into a scope to do time domain sort of correlation with things that might be causing problems, right? Look at other signals that are affecting me. So that's one way I think that's great for kind of isolating and capturing these signals is that sort of frequency mass trigger. Then of course there's a sort of standard power level trigger. So you can also, as I come down into the screen, you can look at only capture your highest power signals instead of lower ones, or look at it in frequency space as well.
How is the user interface on that for people that don't use it every day? The spectrum analyzers.
Yeah, I think so. I lost you a little bit at the end there, but so these are all touchscreen.
Try to feel into where you need to be than it does to actually do the test. This one looks a lot easier.
Yeah, it's certainly every analyzer is a little bit different, right? I absolutely agree. I think this one, these are now touchscreen boxes, so you can capture the mode you want and move them around, and I can move things with my finger on the touchscreen as well as the menus. But there are 10 or 15 different kind of buttons on the display as well for different kind of mode and operations. So I think like everything, it takes a little getting used to. But most of the time, we're working in different kind of ways. So I guess the the neat thing about these instruments is that, well, as we kind of talk through it here, there's like 4 or 5 different modes now, which kind of changes kind of how the setup. So instead of going deep into menus to find some of the functions, you'll just switch a mode, and that'll give you a little more high-level access to some of those features. So I could have done that a little more obviously by, you know, you can using just the touch screen instead of the knobs, right? You can move around and look at the frequency, span, amplitude, so you guys can see it a little better. And if I needed to, I went over to the trigger menu, hit the trigger button before, and then I can capture those signals in that mode as well.
Okay.
All right. So that's the kind of thing I do to really isolate those signals as well. And then I think the other interesting visualization mode that's capable here is because of the speed and the way it pulls the data in time domain before translating it to frequency, you can also get some really interesting sort of time domain views, right? So you can look here where we're looking at the power over time, as well as, you know, the spectrum. And in this case, looking at the waterfall on the side here. So that allows you to look at different, you kind of see the modulation, the time modulation, right? So if you're working with some, you know, ultra wideband signals or some other time demodulated signals, you can easily kind of see, hey, is it moving? Is the amplitude changing over time? How is this being modulated if it's not just in the frequency domain? Now, if we do that with our frequency signal that we're kind of built in on here, it shouldn't be terribly exciting, but I'll do it anyway. So now we can see that. So as you kind of would expect, right? It's an FM signal. So within the band of the detector, the amplitude is roughly the same across the board. It'll change a little over time depending upon what song's playing here, but in general, it's not really time demodulated, right? It's moving in frequency space. So it's best to view kind of in this waterfall arena. All right, so kind of, moving on from the sort of spectrum monitoring kind of core application over to some other techniques that I think are real popular, just with debugging and setting up rigs and things like that. Obviously, one of the big ones is antenna characterization. Oops, trying to get this off the screen. So I gotta open the chat too so I can see that. So the antenna characterization, obviously, guys, you're making VISWAR measurements. There's actually a couple different ways to do this now. One, you can do it with a VISWAR bridge, like is shown there. On the newest instruments, where we'll talk a little later about the new VNA capabilities. Obviously, those have a built-in differential coupler on the tracking generator that allows you to make direct VISWAR and return loss measurements. So a great way to look at different, make sure your antennas on your rig are doing what you think they're doing. And the combination also of the tracking generator and the analyzer here allow you to do some real clean sort of filter testing type measurements, right? So you can look at output, frequency output across from the output of the device and measure its response over frequency for whatever type of whether it's an amplifier, attenuator, filter, whatever. But obviously, if you guys haven't used one before like this, right? Obviously, what we're doing is the tracking generator. This is in the scanning mode. The tracking generator is always synchronized with the analyzer, so it works across the span, putting out and reading back the power at each frequency. So you get a nice sort of response curve across frequency.
Hey, someone asked in there, what version of the scope are you using here?
Yeah, great question. Sorry. So what I've got, most of these slides are about the 5000 series. These are the really real-time spectrum analyzers in general. What I'm using in front of me here is an RSA5000 TG. So that's a 1.5 gig real-time analyzer that's running about, it's probably about $2,000 these days. You know, when we're talking about some of the VNA capabilities, you know, those are the models that end in N now. So that would be yeah, thanks for putting in the links there. Yeah, those are at T Equipment, or you can capture it us at RIGOLNA.com as well, where we keep our information. So the RSA 3015N is probably the kind of newest, you know, real value one at 1.5 gigs that has all the VNA capabilities, has the built-in differential coupler to handle the S11, S21 distance to fault measurements. And then as you move to the 5000 series, you have some of the advanced capabilities that we'll hit on briefly, like the complex demodulation for IQ signals, IQ demodulation, and the that's the real difference, is the addition of that option as a module.
Chris, this is Paul Cloud, KF5CKQ. Sorry to jump in the middle of your
No,
demo
please.
there, but I am very interested in these VNA features, and I'm also interested in your MSO models because I really feel like that gives a ham radio operator multiple options in one box. Are you going to be discussing those at all?
Yeah, we certainly can. I was keeping it pretty open. Was hitting some spectrum analyzer stuff, but here, for instance, I have one of those set up too. Let's give me a second to switch my wires around and see if I can do it. There we go. So that is the, you know, that's an FM signal being pumped into the MSO 5000 oscilloscope. So obviously here I've done a sort of Keller graded FFT over top of the primary signal to show that precise modulation there. So we're seeing it between, you know, sort of, you know, in the 0 to 10 megahertz span here. This is a 70 meg scope, but just a little modulation signal I put in there on the FFT. But obviously, if we turn that off, we can then look at that, dig deeper into that modulating signal. And at a certain time there, we saw see some of that modulation, but you can scroll all the way into the individuals here, and let me set my triggering up. Sorry, you can see that frequency modulation that way too. And if we wanted to, we can, you know, turn on some of the precision measurements to look at the frequency. These are touchscreen now too, so you're kind of watching what I'm doing. Statistics are on. I want to go ahead and turn on precision measurement mode. That gives it a look at the deeper data for making those frequency measurements. And so we can see here the frequencies changing here between 3 and 7 megahertz, essentially. It's a sort of standard sinusoidal FM modulation. Now, if I change the modulation to, you know, square type, then there's very little in between. There's just 3 and 7, right? Just moving fast between. You can see the different modulation schemes and how they look slightly differently on the visualization on the scope itself. So that's sort of the MSO 5000, which is, I think, a great partner using our latest front end technology on the scope side.
Yeah, Chris, can you talk a little bit about what kind of cost there is in these? I mean, I see that these are out there. They go up to, it looks like about 350 megahertz or maybe higher. I haven't done. I'm just running a single monitor here, so I'm having to switch back and forth between the presentation and the website if I want to look at that. So I'm
In words. Yeah, this model, the 5000. So I guess the way to think about it in terms of you're looking at our technology, right? The 5000 is the entry point for our custom ASIC front end, which gives you, I think, the latest technology and some really nice capabilities and features. I mean, we're talking about, 100 million to 500 million points of memory depth, 8 to 10 gig of samples, and really, I think obviously a great kind of UI. It's all touchscreen and all the functionalities you need. And kind of as you may have noticed, both these instruments have HDMI out, which I'm pumping into my computer to put them on the screen here for you, so you can look at them. I often just use them with a big display on my desktop if I want. So I think the MSO 5000 started about $900, I think, 909 or something like that. And this technology can go up to $10,000 if you want a 2 gigahertz 8000, right? So that's really kind of the range we're talking now. But I mean, that's what I think Regal's done for the last 10 years. That's, I think, been exciting and interesting from a consumer perspective. Is we launched new things, and the in the old days when you launched new things, the prices would go up. Here at Regal, we launched new things and they're cheaper than the ones that came before. So it's really this test and measurement market has become a lot like the TV market, the laptop market, where just the ability to innovate has changed the parameters of the market so much that new less expensive things are coming available really all the time. I think for you guys' perspective, if I'm a ham doing this, I think the one thing to note is that the 5000s don't come with a 50 ohm input by themselves. So you either would want a 50 ohm adapter on it to look at true RF signals, or move up to the 7000 series where you get 50 ohm in the front end, right? So or just be aware that, hey, you're not moving power like you normally would because you're not in a 50 ohm system anymore. You have a high impedance input here. So cool. Any other questions about that? Yeah. So just kind of from a we talked a little bit about the POI and the speed on the kind of the hardware capabilities, if you will, of the real-time spectrum analyzer. I think the analog, the analogy for the oscilloscopes would be what we call kind of waveform capture rate, right? Which is how many waves can it put on the display per second to give you, so you don't miss, those transient signals, right? And these 5000s and this technology set, really gets up to 500,000 or 600,000 waveforms per second on the display. Captures data to the screen per second. So you're at a point now where you're really not missing any sort of aberrant signals in any real sense, and you've got you're getting 20 or 50 times the amount of information to the display that you were a generation ago with a starter scope.
I don't want to speak for everybody else, but I personally want to thank you for presenting today. This is really exciting, and I had no idea that the price points were where they are, and I probably wouldn't have looked because I'm used to what they used to be.
I agree completely. That's why we come here, honestly, because I've been doing, like I said, I've been doing this for 10 years, and when we launched the DSA815, the 1.5 gig spectrum analyzer, I think 7 years ago, it started at like $1,500, and it was fun to talk to people because they all expected it to be $15,000, right? And those dynamics have changed a little bit, but I think Regal still is pushing the envelope there on what we can do and what's a reasonable price. So there's nothing more fun than talking to people and telling them all the cool things the instruments can do, and then blowing them away with the price.
Thank you.
Anytime. Cool. So yeah, I mean, obviously, guys, free flowing discussion's better for me if it's better for you. Happy to chat about or look at anything you want to. Go ahead.
We were you were talking about the vector network analysis capabilities of your real-time spectrum analyzers. That's something else that I'm interested in. I mean, I use an older product from a competitor from Agilent to do vector network analysis. It's quite a bit larger. So I'm kind of looking at what you've got to offer, and it looks like a really interesting product. And so you were just starting to get into that when I threw you off onto this MSO thing, and the interest for me with the MSO is that it does give you lots of capability in one box, but obviously you don't have I don't think you get the noise floor of a good spectrum analyzer on an MSO, and I don't know about it just seems like it seems like that VNA capability is going to be an interesting thing for people to talk about. I realize that the real rage in ham radio right now is the ultra cheap little, pocket VNAs that have come out, but I don't feel like they have the capability that a good desktop instrument can have. And honestly, you guys' instruments are about the size of what we used to consider a portable instrument to take out in the field and do field measurements. So I'm going to have some interest in that if you're going to have any time to discuss that.
Yeah, I think we'll definitely hit on that here. We can move to that shortly. I guess your instrument can't be that old if it says Agilent on it, right? The HP ones are the old ones now. The Agilents are middle-aged, and the Keysight ones are the new ones.
So true.
They keep changing, but yeah, I guess like just a couple while we're on the scope here. I guess a couple quick notes about this guy is the other nice thing about, I think, the way RIGOL does this is that we've got we're giving away essentially all the options on these scopes these days. So when if you buy a new RSA5000, you get the 2-channel arbitrary waveform generator built in, turned on. That allows you to do Bodie plot frequency analysis as well. So you can look at filters and do I guess the first look at what we talk about when we talk about kind of network kind of analysis, right? You can look at gain and phase over frequency with a scope like this with the built-in generator, and then we also turn on all the serial decode capabilities as well, so I2C, SPI, and all on the power analysis and all those functions that I think make it a really valuable kind of option for people doing different things.
Yeah, that logic analysis functionality for a lot of guys that are doing Raspberry Pi work, that can be very useful because you can look at your ports on the Raspberry Pi, what your signals are in and out, and do all of that on one instrument screen. So I think that's some very good capability. I'm happy that you throw it in. I also want to say thank you for doing this presentation. I'm very impressed.
My pleasure. Thanks. So yeah, I agree with that. I think I think that's a great kind of, if you're in the guts of a Raspberry Pi or some embedded technology sort of development, right? I think the ability to look right at that bus and say, okay, here's the byte order that's coming across. So when I program it to send out a little ASCII string to my device on the other side, this is exactly how it's being encoded and transferred, and this is what's happening. And that's, I think, a great way to look at those signals and see noise and issues that are rising up. So yeah, I do that for a amount. All right, so kind of then I guess I'll skip over. I'll just skip over some of this for a little while, and we can come back and talk about EMI if we want later. But let's while we're on the subject, let's hit a few of the advanced kind of measurement modes, which is especially the vector network analysis, which is available on both the 3000 and the 5000, and then the Demod, which is up on the 5000 series. So I just put a couple examples here that we could talk through, but what we're able to do, again, with because of the technology built into the box, the tracking generator with the built-in differential coupler allows you to look at a couple classic S parameters in a network analyzer mode. So you got S11, S21 measurements, and then we'll look at the reflection of our distance default measurements. Did I do that? Someone writing on. Okay, so so typically, obviously, your Smith charts are kind of classic way to look at this data, and this is what's so obviously we're talking about in general, we've been talking about frequency and power. For those of you who don't use them a lot, what a vector network analyzer allows you to do is look at frequency, power, and phase, or change as a modulation of that phase. And there's a lot of interesting sort of data to be built up from, or I guess diagnostics to be done from, how are these complex RF circuits, altering that phase and what it means. So Smith's chart is sort of the classic way to look at that impedance analysis, but obviously you can also see how the phase is being adjusted. Look at the VISWAR, standing wave ratio as well, or just look at the magnitude over frequency. So there's built into the VNA mode, there's 8 or 10 different sort of visualizations, and these are kind of the key ones, I would argue. And then the distance default is the using this kind of same technology, right? So we're pushing out a signal out of the tracking generator and looking how it reflects, and using some different math there, we're able to kind of pull it apart in time and see, okay, how far from the input of the instrument is where we see a kind of a real reflection or a high power reflection, and that's how we talk about capturing. Hey, I've got my having some trouble with my rig. I've got my my cables going up to the antenna on the roof, but there seems to be some kind of problem. Where's that problem? Well, you can look at an instrument like this, can show you, well, the problem appears to be 4.5 meters from the where the instrument is, or 8 meters out, or 10, right? So it tells you which coupler, connector, or transfer, or where the squirrels have been chewing on the cables, right? So that's I think an interesting application for just, again, different ways to debug these kind of RF systems that seem interesting.
Hey Chris, on that distance default, do you have multiple coax types programmed into your system? Is this something where you can set it to do distance default in feet or meters? Those are specific issues that I run into with instruments. So that was one of my questions.
Yeah, there's absolutely. I guess I don't have it on my live instrument here, but yeah, there's this. You can set it for meters or feet. There's a setting for that. In essence, it's a velocity factor setting. So you can alter the velocity factor, and that tweaks the distance based on the type of cable that you have. So as long as you kind of know what your what the velocity factors are, or obviously you could set a cable length and then tweak it to match. So you kind of debug the velocity factors. But that's how the math is really done there. Those are the big levers to pull, are the velocity factor kind of, which is really a material science sort of calculation.
All right, thank you so much.
My pleasure. I guess one thing to know about the VNAs is that there is a cal kit that you typically want to have, and you can use your own cal kit because you can adjust the parameters as well. But there are a couple cal kits that to really make any accurate VNA measurements, you have to cal that setup essentially every time, right? So you want to do that to make sure you're getting good results. All right, so I didn't throw anything else in here about the VNA, the vector network analysis. Just put a couple details in about the signal demodulation. Assume this is a little more far field from what most of you guys are doing these days, but I think it's an interesting sort of way, again, another way that we can pull that data apart and analyze it, right? So if you're looking at a signal with sort of standard modulation formats like these, you can bring it into a mode where you're pulling that data in and you're setting the bits. So you're looking at the actual data being transmitted. and you're looking at the constellation diagram, so you can see how much noise, what kind of noise is in that system, and allows you to debug those kind of range and signal issues too, right? So as you know, obviously as you get your antenna gets worse, you get farther away from the source, your whole spectrum falls down, then you get more noise in the constellation diagram that starts to affect your bit rate. And so if you know the signal you're transmitting, you can go all the way through this process and say, okay, I'm expecting, you know, this 100-bit sequence, and this is the one I'm getting. So you can do error rate analysis. You can set it up to trigger on a bit sequence to start, look at the whole sequence and compare the error rate, which again, you know, for people doing kind of you know, Raspberry Pi or simple modulation build outs, you know, it's a great way to debug, hey, what's my actual signal quality in a, you know, bit error rate mode, you know, at this range or at this power level. And always, when we talk about this a lot, sort of in an IoT sense of balancing, you know, battery life, range, power, and, you know, how many times we have to reset data because we lose bits, right? So it's all wrapped up in that game of optimizing your Internet of Things type projects. All right, so now those are kind of the high level functions I want to talk about. So I guess I'll go back a few slides and talk about, we talked about filters and you know, phase noise is pretty straightforward in this sense. So let's go ahead and I guess the other application that we talk about a lot, and that I think a lot of folks are interested in these days, whether in IoT or kind of development work, is really DMI pre-compliance, right? So, you know, the availability and cost of these spectrum analyzers having come down so far, what it's caused is you know, over the last 10 or 15 years, folks who used to, you know, their engineering process used to be, well, we'll do our best building out this product, then we'll send it off to the compliance lab, and they'll tell us what's wrong with it, and we'll try some more. We'll put some tinfoil on it. We'll put some ferrites on it. We'll fix it up, and we'll try again in an iterative process. But you know, when you're spending, you know, often $3,000 a day to have compliance work done for you at a lab, you know, now these days customers spend less than that on the instrument, and they do 3/4 of that work at home, with the goal being they can pass compliance the first try at the compliance lab and save money and time on developing their product. So we talk a lot about sort of this iterative EMI pre-compliance, where, you know, looking at the emissions coming off of a board you're developing and trying to get that way, get through your development process faster. And that really always starts with again, a broad scan like this, where, hey, you're looking at peak detectors and holds, you know, long-term sort of max hold, I often use near field probes or a small antenna array, some kind of typically I would use a near field, you know, enclosure of some kind. So TemCell, something like that. So different ways to look at products depending on what you're looking at. But, you know, in the end, start with this, look for signals that might be of interest. And then, you know, I often can go into real time and capture them there and look at different ways to isolate those signals by seeing how they're modulating, right? Are these, you know, so signals like this, these are more constant, right? Because they never appear, or very rarely appear, down in the lower ranges. Some of these signals we can see are turning on and off part-time. So you can use to see how they're modulating. You can often use the waterfall chart as well. But, you know, these clock harmonics like this, you've got, you know, different signal types you can debug with a real-time process like this. Talked a little bit about frequency masking as well before, so that's pretty cool. So then, again, we can use the power versus time to look at different modulations and figure out a root cause. Is it a clock? Is it a modulating signal? What's it really doing? And then finally, we get into sort of EMI mode, which is another operating mode for the spectrum analyzer, where it's really set up more like an EMI analyzer, where you've got your scans with limit files on it. You've got signal table, and then you've got the sort of bar graph look of, hey, with a peak detector, quasi-peak, cis-per-average detector, what are the different levels you're actually seeing here? So the kind of process there is, finding signals that might be annoying, looking at them, and then really analyzing, hey, are these going to be problematic in a compliance sense? And sort of in real time debugging, how do I change my enclosure? How do I tweak my firmware to improve these signals so that I can pass a compliance test? And then I think there's a little more detail about that. So again, we talk about I usually use a peak detector, an EMI, cis-per-average, and a quasi-peak detector on here. So I'll capture peaks of interest. I'll highlight them, go right to that signal in real time, and kind of look, okay, is that signal going to be problematic when the compliance lab is using their quasi-peak detector? And of course, all this is built into the grand scheme of, you probably don't have a full compliance lab setup or room at home, right? That would be unusual. So you're trying to correlate data in near field space that doesn't really mathematically correlate with what they're seeing at the compliance lab. But you can compare good known good products and test mode products as you move through iterations of a development, and to see how those signals change, where signal peaks or quasi-peak signals come up out of the noise and start to get close to your limits or your bands. So I think it provides a great tool set for sort of limits and margins that allows you to, in essence, build confidence that you're not going to have a problem at the compliance lab over time. And there's just a quick look at the scan table. And again, this newest kind of version of the MI mode is all built into the instrument. So you can do it from the front panel with a touch screen. If you have this out in the field, right? The newest firmware version on all these analyzers, the ends especially, allows you to turn on a web control module as well. So you can put it on the LAN network, and you can see the same screen as you would on the front panel on the web browser, and use the mouse like you would the touchscreen. All right. Well, I think that's all the slides I put together. Any other anything people want to talk about, or anything else I can help with? I think you're on mute, Paul. I don't know if you're talking to me. Okay, there you go.
Yeah,
I still can't hear you, Paul.
How's that? I said I feel like I'm monopolizing the conversation here, but so on your instrument there, the 5000 is, what is the maximum signal strength output on the VNA, and does it have a built-in DC block on the input? I'm sure dig all this out of the specs online, but I'm just kind of trying to figure out, if I'm interested in getting something like this to take on site to go work on a repeater or something of that sort, what kind of power level am I going to get out of the tracking generator?
Yeah, tracking generators are usually, they're set from either -40 to 0 dBm.
Okay.
So you get up to a milliwatt out of that.
And then what's the noise floor on the spectrum analyzer typically?
So I guess we usually talk about it. Obviously, displayed average noise level, you can get down into minus 160, 165 type area. I think there's for S11 measurements, we specify the dynamic range at, I think, 80 dB. So,
right.
So I think it's a great instrument with I think a good design for noise floor. With different sources and different ways to look at it, certainly, but You can, once you optimize the view for the kind of the noise and the signal you want, I think you have lots of options.
All right. Well, thank you again for doing the presentation and showing us this gear, and I've truly enjoyed it. I was kind of looking through the RIGOL NA website, you know, trying to figure out what the products were and what the levels are and what the specials were here at the end of the year. So it's a very interesting thing to look at, and I sure appreciate you coming and giving the presentation for us.
Sure. I guess I'll give you guys one other hint. I think starting on Tuesday, we're going to be doing a little clearance blowout of some of the slightly used equipment. So if that sort of thing appeals to you, I think we're going to put 40 or 50 models up at 40% off on the clearance site sometime on Tuesday morning. So yeah, happy to, I guess the other thing I'll put up here is, so we talked through that, but really there's my email, my phone number on the right. On my screen, it's got a little red slash through it, but that's okay. It's there you go. So so you can always drop me a line if you want. Happy to chat through anything, any questions you have, or any of our folks here can. But yeah, that's where we are happy to help.